Okay, so share. Okay, is my desktop visible?
Yes, sir.
Yes, sir.
Okay. Then where is the conversation? Okay, let me keep it on. Okay, so today we will solve a few exercises on push down automata and some related topics in context-free languages. First of all, I have already explained this context-free grammar for this. Okay, so we've explained in the last tutorial. Let us do something new. Okay, so in a very similar line, let us do this. So you're comparing number of X and number of B's. Now you're comparing number of X with twice the number of B's. So to start with, design a context-free grammar, and then we will design a PDA. So any suggestions? S to every permutation of AS BB. This will possibly not work, but why? I don't have the case where string starts and ends with B. No, I can have BASB. Okay, so now another suggestion has come. Okay, maybe this will work, but question is why? When you propose something, you are required to give some kind of proof, right? Yeah, maybe this will work as a... No, don't try like that. So assuming that something will work. Have something in mind why this will work. Well, you include things like that, that's fine, but why will it work? That is the question.
Sir, like for every for every B inserted, we'll insert 2S in the same step.
True, that is true. For every A, somewhere you have to insert 2 B's. But does it cover all the cases?
I think so, yes.
Anyway, you may try to establish this by induction. So I will give you an alternate way of doing it, which will actually require as such no proof, because the proof is evident from whatever I am doing. So what I will do, I will have 3 non-terminal symbols, S, let us say A and B. This S is our desired thing, number of A's equal to number of B's. A will generate just one more A, and B will generate just one more B. Fine. So I have to do an interplay between S, A and B, and eventually design a grammar simultaneously for all of these S, A and B. But in order to see that my grammar works, now let me define this. Now there is a surplus function which is no longer number of A minus number of B, but two times number of B. This is my surplus function in this context. Okay. So now if I again look at the graph, so at the end I must have surplus equal to 0. Initially also I have no A's, no B's, so the surplus is 0. Now let us see what happens. So you are at some point and one A comes. The next symbol is an A. Then the surplus function increases by 1 because the number of A's increases by 1. Okay. So next symbol is A. And the surplus value. And this increases by 1. But if a B comes as the next symbol, what happens? If a B comes, what happens? What is the change in the surplus function?
It decreases by 2.
Decreases by 2. So this is like a continuous function, but minus 2 is not really continuous. Okay. So that creates a trouble. So in order to work around this problem, let us, as earlier, let's consider two things. If it starts with A, then the surplus function becomes plus 1. Now from plus 1 to zero, okay, the surplus is minus 1. So if this case occurs, I can say, of course, S can be epsilon. This case you handle. If it starts with A, whatever follows must be an instance of B. On the other hand, if we start with B, then what happens? The surplus becomes minus 2. From here, I want to reach 0. But you see that increment is continuous. So there must be some point in between where from minus 2 I go to minus 1, and there must be some point. Okay, at the end it's 0. But if I look at this string from here to here, this is an instance of what?
Occurrence of A.
A. Just one more A. So from here to here, it's another occurrence of A. So this is fine. This is for S. Okay. So now that I have introduced A and B, I should also be able to write the grammar, the productions for A and B. Okay, so let us look at A first. This is A. So I start at 0. I will end up at plus 1. Okay. Once again, I consider two cases. If I start with A and if I start with B. If I start with A, what is that follows? Yeah?
S.
Yes.
Yes.
Good. So start with A, this. If I start with B, From -2, I have to reach +1. So somewhere there must be, so increment is continuous, so it must be somewhere I must reach -1, somewhere I must reach 0, eventually 1. So it must be B, A, A, A. Happy? Of course, this A cannot be epsilon. So this part is fine, right? Now finally look at B. Where do I use B? Maybe here. This is for B. So you start at 0. Just we have one more B. So I will eventually end up at -2. Agree? So in this case, if I start with B, it is already -2. Then whatever follows is S. If I start with A, somehow I have to reach from +1 to -2. Right?
Sir, don't we have to reach -1?
Where? In this case?
Yes, sir, for B. Like B defines that number of A should be equal to number of B minus 1.
Professor Das, I think there will be a 2 before the number of B's in each of the things.
No, maybe I'm making a mistake, but I do not understand what you're telling me.
So you have written number of A's equal to number of B's. It will be, I think, 2B, 2 number of B's.
Yeah. Here these are all. Sorry. Yeah, it's trivial mistake. So I hope this has not created much confusion. Yeah. Because this 2 is involved here. Yes. Sorry. Okay. So if it starts with A, I am here. Okay. So now I have two possibilities. One possibility is that I may reach 0. If I reach 0, then from +1 to 0, it's an instance of, +1 to 0, it's an instance of nothing.
Sir, it should end at -1.
-1, sorry. Oh, sorry. So that's the problem. Yeah, it should end at -1. Yeah, number of A's is just -1. Sorry, -1. Good. Yeah. So one possibility is that somewhere this will decrement from +1, it will reach -1. If it touches 0, then what is this part?
Capital B.
Capital B, right? So if you start with A, one possibility is this is capital B, and from here to here, once again capital B. Okay, but it is also possible that this 0 is never reached because the decrement is by a factor of 2. So it may be that from +1, I directly go to -1. This is a possibility. But then, what is this part?
Small b.
This
Oh,
is
sorry,
small
S.
And then, from here to here, we have another S, right? And here I have a B. Okay, so that's the complete thing. And the way I have constructed this graph is essentially I am doing the same as an inductive proof. So if you are given this set of rules, I can always parse an element of S. Okay, is that correct?
Sir, when we start with small b, when we're doing capital B, like it should be capital A, right? Because there'll be a -2.
Oh, yes. Yeah. Earlier I was thinking this is minus 2, so this is capital A. Yes. Thanks. Okay. This is capital A. Okay, capital A. Fine. Yeah, so you see that arguing this way, it's much easier. I would not say that whatever grammars you have proposed will not work. Maybe some of this will work. Maybe with little bit modifications, but that requires a proof. Okay. Here the proof is obvious because my construction itself follows the, I would say, inductive proof. Fine. Okay, if that is the case, let us move to designing a PDA for this. This is going to be a somewhat easier task. Yeah, design a PDA. So one second, let me write Sx is this. So essentially the PDA will keep track of this as it keeps on reading the input symbol by a symbol. What do you think? Acceptance by final state or stack, empty stack? Which one is more natural here?
Empty stack.
Empty stack.
Okay. In this stack, essentially, you will store this value as a sequence of pluses or as a sequence of minuses, depending upon whether this is positive or negative. So, in fact, I believe only one state will do. Let us see. Let us try. So initially, the stack bottom is exposed. It may also be exposed somewhere in between. If that is the case, and I read an A, what should I push?
A plus and
Plus.
the bottom symbol.
Yeah, plus and the bottom symbol. And if that is the case, the bottom marker is exposed and a B comes.
And then minus bottom symbol.
Minus bottom. If A comes and already a plus is there on the top of the stack, replace it by another plus. And if an A comes and you see a minus,
And an epsilon.
okay, A minus is just an epsilon. correct, no problem. So 1 minus and 1 plus cancels. B, and let us see a minus. Let us handle
3 minuses.
3 minuses. But if this is there,
Then 1 minus.
mm,
Actually, no, that is not true. That is not true.
this is bad thing. Okay. So for this, I have to do something little bit. I have to look at another symbol. Right. So
Like, I think we can introduce some symbol like, I don't know, star, and then have an epsilon transition to take care of removing
yeah,
another.
yeah, either do that
plus.
thing or introduce a new temporary state. That is
Uh-huh.
also right.
Yeah, but
So
if we have it on one state, sir, then I think we can directly convert it to a grammar also.
we can convert it using any synthetic conversion mechanism. If plus, then you first empty it, go to a temporary state. So we have to handle another minus, another subtraction, right? So from here you will come
Yes, sir.
back. If this is an epsilon transition, if the bottom marker is exposed, then you just put 1 minus sign. Now you can see that it cannot be minus sitting on the top of the stack. Because earlier there was plus, below that it cannot be minus. It's either a sequence of pluses or a sequence of minuses, right? So it is possible that another plus is sitting there, in which case just forget it. Now is it fine?
Yes, sir.
And eventually when everything is red,
Pop, yeah. End stack symbol.
that thing up. So that's it.
So that is why we need 3 literals in the grammar, right? Because we have effectively 3 literals over here. I mean, 3 non-terminals over here.
Yeah, small.
Plus, minus, and 1 for the other state.
Yes, gamma is plus, minus this. Yeah, that's true. Of course, you can call them UV, PN, whatever, but something like this. So this is acceptance by empty stack. You should mention this. Okay, no problem with this, right?
No, sir.
Okay, fine. So this operation is clear. So now let us move to something slightly more complicated. It's of the same type of flavor, but now I want the number of A's or number of B's to be sandwiched between the number of A's and twice the number of A's. Now a single surplus function is not really that good, right? And designing a grammar for this is not going to be straightforward using this kind of principles. Okay, because I do not know how to define a surplus now. Number of A minus twice the number of B, number of A minus twice, or just minus number of B, because you are comparing the number of B's with both number of A's and twice the number of A's.
But sir, can't we brute force it, like first design a PDA and then convert it to a grammar, like from the construction you showed in class?
That always you can do. That always you can do. But the reason why I have introduced this exercise is that sometimes it's much easier to design a PDA than a grammar.
True. Got it, sir.
Okay, so that's the reason. So what should be a PDA design principle in this case? Or maybe earlier it was A is twice the number of B's. So just to be, I would say, consistent. Maybe I just change these two things. Text, twice, text this. Let me just swap the roles of A's and B's. The same language with only A's and B's swapped, so that it looks like the previous one. Ax equal to twice Bx. Yes. Yeah.
So like for A is red, we can add pluses, and when we read a B, we can either well, if it's greater than or equal to B, then we remove one B, or we remove one plus, or we add, no, that doesn't work, or add two pluses. But I think we'll need two symbols for that. One symbol will not do.
Track. So A is between plus B and 2 times B. So they are possibly more numerous. So for each A, I will make a plus 1. And that can be affected by looking at the top of the stack. If it is the bottom marker, just introduce 1 plus. Okay. So it's something like this. If you read A, you see this, introduce a plus. If you see already a plus sitting, add another plus. If you see a minus, just take it out. Now what happens if B comes? So if I look at this equality, number of B is equal to number of A, then when a B comes, what you would do? Minus 1, right?
Yes, sir.
On the other hand, if I have this equality, number of A is equal to twice the number of B's, then if a B comes, what will you do? Minus 2, right?
Yes, sir.
Yes,
Here
sir.
I am sandwiched between the case for B, it may be minus 1, maybe minus 2. In fact, you can see that all combinations of minus and 2's will work. If every time you do minus 2, minus 2, minus 2, then this is the equality. If every time you do minus 1, minus 1, minus 1, you have this equality, equality here. And if you choose any other combinations of pluses -1 or -2, then you end up somewhere in between.
So we do both, kind of. We split the state and we do both.
Yes, not exactly. So for B, non-deterministically, do either -1 or -2. Okay, so whenever you see B, you make a non-deterministic decision whether you are going to subtract 1 or 2. So this case is already handled, and -1 case is actually easier. So in this case, what do you have? B, this is there. Then it is minus. If a plus is sitting, just kill it. Minus is there. Minus, minus. Alongside this set of transitions, I will also have transitions of the form now this case is a little difficult. From B, you have to go to the temporary state. Okay. Okay. So I will also have a transition. Okay. So whatever I have written there. So B plus epsilon and then these two things. Whatever you have seen here. This thing and this thing. Okay. So I will have both these transitions and these transitions. The machine is free to choose whenever it sees a B, whether it will take this transition or this transition. It sees plus, it just decides whether it will take this transition or this composite transition. If it sees minus, it non-deterministically decides whether it will take this transition or this transition. And using
So
this way,
for
yeah.
the B comma stack, the first transition on the right, don't we push back the stack bottom symbol?
Where?
B
Oh.
comma.
Yeah, sorry. I meant this, right? Oh, sorry.
2 minuses and 1 stack symbol, I think so.
Yeah, that's true. I will just correct this. This is just a typo. Yeah. I hope I have not made the same mistake here. No, this is fine. Yeah, so this is just a typo. Okay, so I will have both these two rules. This and this. This and this. Whatever the machine chooses, it will end up somewhere with the count of A's in between this, both inclusive, these two ranges. Okay, so guessing is an important part of context-free languages and in particular push-down automata. This is fine, right? This construction?
Sir, how are you accepting, like by empty stack?
Yeah, and this is also by empty stack.
So like in the end, if you have extra minuses or pluses, we pop them off?
No. If we have extra minuses or pluses, it may be just a bad sequence of guesses.
Okay, fine.
But if the number of A's is strictly between this and this, okay, it's not strictly in this range, then some guess will allow the machine, some sequence of guesses will allow the machine to end up with an empty stack. Yeah, that's an important thing. If the guesses are incorrect, then there may be some surplus pluses or minuses left in the stack. But that is fine. It was just a wrong guess, wrong sequence of guesses. But if the guessing was correct, the machine will end up with an empty stack. And of course, you will have this at the end, epsilon base this. and nothing else needs to be read. Okay.
Sir,
So-
the two cases which you have shown, they are take that for -1 and -2, they are taking into account the two conditions when number of A's are equal to number of B and number of A is twice the number of B. But are we taking into account the inequality part?
Yeah, the point is that at any point of time, whenever you see a B, you have a non-deterministic choice. Suppose you have this. Okay. It is saying the bottom marker. Now this transition is possible. This transition is possible. Okay. So on some instance you take this, on some other instances you take this. On some instance you take this, on some other instances you take this. Or this. So any combination is allowed, right?
Okay, sir.
Okay, sometimes -1, sometimes -2. I do not say either this is exclusively this set of rules or this set of rules. Both are there, both are allowed. Fine.
Yes, sir.
Okay, good. And then, of course, if you have some such rules, then you can use a mechanical procedure in order to convert this to a CFG. I have not tried that conversion or generating any CFG from the first principles. Maybe you can try. Okay, let us, I do not know how easy it is. For PDA, it is more or less clear, given that a PDA can always guess how many times it will do -1 and how many times it will do -2. It's up to it. Okay. If these counts are appropriately guessed, then it will end up in accepting a string in this. Good. Fine, right? Let us, okay, so I will switch to the next one. I think this is once again, yeah. So design a PDA for this language. Have you already seen that this language is the complement? This A and B and C N is definitely not context free, but it's complement in ABC star. This is context free. Why?
I think it's a union of a couple of context-free languages.
Union of many things. First of all, one is strings containing, let's say, BA. Right? Strings containing CA. Strings containing CB. So they are actually even regular languages. Okay, so basically strings containing. Other than that, if we consider strings of the form A star, B star, C star, there are two more parts. It will accept all strings of the form A power I, B power J, C power K, such that I is not equal to J. It will also accept all strings of the form A power I, B power J, C power K, J not equal to K. So the complement consists of these 5 parts. The strings containing BA, strings containing CA, strings containing CB, and these strings. Happy? So my PDA, what it will do, it will initially guess which case it is going to handle. It may be either this case or this case or this case or this or this. Okay. So To start with PDMX and epsilon transition. From this state, it will simply keep on checking a pattern BA, checking for a pattern BA. And it has no necessity to I would say, use its stack. Every time it will be bottom marker / bottom marker. Okay. Here also it is just checking for CA, checking for CB. And here what will you do? I not equal to J. So this case 4. Let us see case 4, what happens. So this is same as this. So in this stack, you have to remember this I. So what will you do? As long as you keep on seeing A, you push something. This is fine, right? Then you guess at some point of time this block of A's is over. And whatever you have, capital A or this, just keep it coming here. Now, what will you do? For every B rate, you take out one capital A, right? But eventually there must be a mismatch. Yes or no? So we'll go to the next state. So what does it mean? I have I is, and then I have started reading B's. There is still some B remaining. And
So J greater than I.
J greater than. But I should also be able to handle I greater than J. Okay. So here what will you do? Eventually I have to somehow consume the C's. Okay. So just consume the C's. Whatever. Sorry. Whatever it is. Okay. But let us be done with the B's first. Okay. There may be further B's waiting in the input. just consume them. But this handles the case when j is greater than I. I should also handle the case when j is less than I. What does it mean? When all b's are red, okay, I must have some surplus a's left in the stack. Okay. So from here, I will make another thing. I will read nothing, but some a must be there. Pop it. And here also you keep on doing the same thing. Keep on popping the surplus a's. And when the bottom marker is exposed, keep it there and go to this state. And here, okay, this is actually running out of space. So here you are consuming b's, extra b's, and here you are consuming the extra a's stored in the stack. And eventually you come here. So this is also an, where is it? Yeah. This is also an epsilon transition. This should be exposed. Here you consume the remaining c's. Eventually this. Okay, so here also is acceptance is by empty stack. This is fine, right? So I have handled only case 4, case 5 is symmetric, and these cases are actually easier. They can always be done using a DFA kind of manner. Any questions?
No, sir.
Good. Then let us look at this. This is going to be somewhat more complicated. The cyclic shift you have seen, right? And we have seen that if L is a regular language, the cyclic shift is also a regular language. That was a part of long test 1, question 2 perhaps, right? Now the same thing holds in the context-free level. So if L is a CFL, you take all cyclic shifts of strings in L and generate this. This is also a cyclic, this is also a CFL. So what would you do to prove this? So if you look at the proof for regular languages, we relied heavily upon the states. So original thing, xy is in L. So after reading x, it goes to the machine DFA goes to some state q. And from q, after reading y, it ends up in some final state. So we can guess q. Okay. Here you guess q, go to a final state, make an epsilon jump to the start state, then read x. If you eventually end up in the same q, you are done. Or it may be like you fix q and then take union over all these possibilities of q. Right, so this is a natural way of doing it in the context of regular languages. Yes or no? Tell something. Is it fine? Actually, the solution is uploaded to the web page. You can go and check.
Yes, sir.
Okay, but in the context of context-free languages, you have to handle another thing. Often the state information is not very important because we have seen many examples where a PDA with a single state can accept anything. Somehow we have to handle the stack. So what do you think we should do? Let us see what you say. Okay, so let us see what is the difference. So the original PDF for L, let's say it accepts XY. So this is my X, this is my Y. At this point, the machine starts in the start state S, and the stack is something like this. After consuming S, let's say it goes to some state Q, and let's say you have a stack something like this. Okay, this bottom marker may or may not be there, it doesn't matter. And at the end, it goes to some state, let's say P, with the stack empty. So I assume that this original PDA accepts by empty stack. You can also assume acceptance by final state, but let us for this moment assume that a PDA for L, because it is context free, accepts by empty stack. So I must have a situation like this. State is S. The stack is currently containing only the bottom marker. After consuming X, it goes to some state Q with some stack content. Then it reads the remaining part. It goes to some state P, and the stack is empty. If I have a situation like this, then the machine will accept XY. But for this language, what I have to do is that I have to start here consuming Y first, then X, and eventually I must end up with an empty stack. Okay. So that problem is little different. Of course, I can guess Q. There are only finitely many possibilities. And it is possible that this original PDA has only one state. So in which case, there is nothing to guess. We have A is equal to Q equal to P. But how about the stack? We have very little idea what the stack may contain when it will read X in the future. Right? So you cannot simply go ahead, read X, prepare the stack content, then you read Y. So when you read Y, you have to do something about the stack. Any suggestions? Okay, so what will the converted PDA do for cyclic shift? It will start its operation here. Okay. At that point of time, its stack is empty, except for the bottom marker. So let me use a different bottom marker, something like this. Then it will consume Y. Definitely this should not be empty, but the operation of the original machine on this part Y is very much dependent upon the stack. Without this, this machine perhaps cannot work. Okay, but this is now unknown. Okay, but don't forget that push down automata can guess. What is the guessing problem here? It may guess this and replace this by this. Then, if it simply simulates this original machine, or maybe it will keep it here, whatever else is there, it will simply guess, okay, by popping arbitrary symbols on the top of this of its own stack. And then if the guesses are correct, okay, then what will happen? After consuming Y, the second part, what will be left? Only this thing will be left. So this is initially guessed, some guess. This can be done. And then if this converted PDA simply simulates this, it becomes this. Okay. After this converted PDA will read this part. So after this, it will come here. Okay. So it now has a situation like this. And after consuming this X, the stack of this machine must be equal to this. Exactly equal to this guess. Yes or no? If that is the case, so after consuming this part, if the machine can exactly recreate the same stack, whatever you started with, this guessing, then definitely we can say that XY is in the original language. Yes or no?
Yes, sir.
Okay, yes. So that is an idea, but the point is that how will it validate? It was its initial guess, because in this part, it has actually destroyed this guess. Right. So after it comes here, how will it validate? I started with this guesswork. So there is a problem, right? Okay, because the guess is destroyed. So this strategy will as such not work. Okay. So we have to do something slightly more, I would say, trickier or more intelligent. So the idea is this: store the guesses. Okay. So the idea is something like this. Something like this. So this is my y, this is my x. Here the machine will simply start like this with only the bottom marker. Okay. Then it will consume the second part. Okay. Now, in order to proceed, okay, certain things are needed here. This will not be guessed here. Instead, what we will do, okay, so if something is needed, I want something on the top of the stack, I do not find it, I will assume that that symbol is there. At the same time, I will simply pop it for the time being, and I will store the guesses here. Okay, so if this guess is same as this thing, then I first store that I have guessed this. Second, because this is a guess, I already have this at the top of the stack, so this machine can now proceed. Okay, and that symbol may be replaced by some other things. Then if you have something on the top of the stack, you keep on processing it, and once again when you see this kind of lead is exposed, okay, so this is actually separated between guesses and the actual stack. And if you see that, you need to make another guess, make a guess, proceed, but remember it below this separator. Okay. So eventually when you come here, you have this, and this is not guessed initially, but whatever is needed is guessed here, and all guesses are stored here. Okay. Now you come here. Okay, maybe you replace this by just introduce this, because this is the bottom marker for the original PDA. And then one by one, you now this machine. Now this is the ideal situation for L to run, this machine to run. Okay. So originally, as this machine runs, this thing will eventually build up. Okay. So now, if I see what happens here, this thing has built up here. I have this separator here, and here I have a sequence of this. Okay. Now, what Cozen says, these symbols are essentially antimatters. These are matters, these are antimatters. Right? So, if I have symbols like A, B, C, something like this, because of the stack thing, the antimatters will be just stored in the reverse order. First of all, you have to convince this yourself. Why? Because A is a symbol because it's last in, first out, right? So A is last in. So A will be first out. And therefore, in this part, A is guessed at the beginning. And as you make more and more guesses, A will move down and down to the below the new guesses, right? Now, if I remove this separator, C and C prime, they are antimatter, so they will immediately cancel each other. B and B prime, they're kind of antimatter, they will cancel each other. A and A prime, antimatter, they will cancel each other. Eventually, you will end up with an empty stack. But there is a catch. You cannot simply take out this separator from somewhere in the middle of the stack. Right?
Yes.
Okay. So I have to do this matter-antimatter cancellation in this process, not at the end, during this process itself. Okay, one by one. But it's already past 1. What should we do? I think this is an interesting exercise. I hope the essential idea is clear, but I have not yet explained how this can be done sequentially, not all at once. So that requires an example. And what should we do? The example itself will take 10-15 minutes time. So maybe let's leave it here. So you think over this on some toy exercises like WW reverse or equal number of A's and B's, how this can be done. Then I will give you a more, I would say, illustrating example, maybe in the next tutorial or maybe on Thursday. That's also a possibility.
Sir, you can make a short video explaining the example and upload it in the course web page.
That also I can do, but you think first. Then whatever is
Yes,
needed,
sir.
you first think. The only thing that I didn't mention, of course, this is a little bit of hand waving, but something that I didn't mention is that this matter-antimatter cancellation can be done sequentially as this X is processed. It should not be done just once at the end. So that's the thing you need to convince yourself. Okay, work on some examples and see that this can be done. Also, I believe this order is fine. If it is ABC here, it should be C prime, B prime, A prime, like this here, the opposite order. Okay, so I think we stop here. Next week also, I think there are quite a few exercises left. These are important, not only for this course, but also for your compiler's course and also for this Turing machine part. So these exercises will continue in the next tutorial session. And if time permits, we'll also do some exercises on Turing machines. So from next week onward, we will start Turing machines. Okay, then think over this.